So moving forward, I'm doing something which I would never let any of my programs do, and it's drinking carbonated beverages before speaking to a group. Sometimes that can be an undesirable effect. Even if you don't have the effect, you might have 2 or 3 hours. So careful with that. We do have an announcement or so. We have tours. The tours are to the labs right around in here. And they are immediately after lunch. If you want to go on the tour, there is no cost for a tour. Unlike in the free state of Florida, where you pay for going anywhere and anywhere. Disney now is over $100, $150 a person. I haven't been to Disney in years. But we've got some great facilities here. They're going to take us around take y'all around. I've got an AAS board meeting after this, but we're going to take y'all around, and all you have to do is sign up. There's a sign up sheet out the desk. Do it when you go out for lunch, and then after lunch, gather there, and I'll take you all on the tour. And we thank you for that. So we've already talked about. Come on down, guys. We have a question that you're already leading us into this. And it's the value of Artemis to science. And we started that with someone saying, well, if you had a really big booster, what else could you do? I think that was in the Venus discussion. So there are lots of things that we can do with things that are coming up. And we're going to talk about that and the value of what's coming up to science and how it might be able to support. Now, SAIC and JHUAPL is sponsoring this session. So thank you all very much. I appreciate it, and the group here appreciates it, and that's great. And next, our moderator for the session is Barbara Cohen. She's a planetary scientist for NASA GSFC. Yeah. I look forward to hearing.
Thanks everyone for having us. Thanks for organizing this discussion. I think this is the first time this week that we'll be talking about Artemis, which is of course NASA's plan to send our next explorers to the surface of the moon, and hopefully this time to stay. And so I'm Barbara Cohen. I'm a planetary scientist at Goddard Space Flight Center. I was one of the co-chairs of the Artemis 3 science definition team. I'm also a PI on lunar flashlight and a couple of these small CLIPS instruments. So I'm the scientist. As scientists, we have a lot of things that we want to know on the moon, around the moon, near the moon, looking from the moon to other places as well. And as scientists, we use the decadal survey process. You heard about that yesterday for astrophysics. The Planetary Science Decadal Survey is coming out literally any day now. And we like to dream big. We like to think of things that we want to learn. And then we leave it to other people to try to implement those things in ways that we have available to us. And traditionally, for planetary science, it's been missions, but opening up the ability to go to the surface of the moon repeatedly with humans with big capabilities like a gateway and an SLS opens up amazing possibilities for accomplishing not just the science that I want on the surface of the moon, but all sorts of science. And that's what we're going to hear today. We're going to talk to you about today. So with us, we have Dr. Sarah Noble, who's a program scientist working on the moon for the Planetary Science Division at NASA. We have Dr. Roberge, who's a research astrophysicist at Goddard Space Flight Center. We have Dr. Ralph McNutt, who is on the staff at Johns Hopkins University at APL. And we have Jake Bleacher, who is the Chief Exploration Scientist at NASA headquarters. And so we're going to talk to you today about the science of Artemis. We'll have everyone introduce themselves and give a brief talk. We'll have some moderating discussion, and then we're looking forward to questions that you have from the audience. And just to set this up, of course, here's the swoosh chart from NASA talking about all the different elements that we're going to need for Artemis, at least in the early stages. And all of these capabilities are amazing. The landers, so many landers. We haven't sent an autonomous robotic lander from the US to the moon since 1972. So it's been a long time. That is my entire lifetime. So I've never had the chance to do this. It's really exciting for me. Having humans walk around, you might have heard some years ago, I also worked on the Mars exploration rovers, and Steve Squires at one point made a very famous quote that said they could do with humans in a month what the MERS did in years. That's true, they cover a lot of ground, they have a lot of autonomous capability, a lot of processing power in their brain. So having crew is a really unique ability for us. And having all of these things up in the sky, Orion, Gateway, SLS, having big landers like Starship that can carry things down and up, those are really cool capabilities. So Sarah, why don't you start us off with what Artemis 3 to geology means?
Fantastic. Y'all hear me? This is very touchy, but I think I figured out how to make it go for it. Excellent. So hello, I'm Dr. Sarah Noble. As Barb said, I sit in the Science Mission Directorate in the Planetary Science Division. I'm also detailed part-time to the SEO office, Exploration Science and Strategy Integration Office, which is where a lot of our lunar science is happening these days, including the PhilIps program. I am also the Artemis science lead, so we're going to talk a little bit today about what we have planned in terms of science. I love this image. As Barb said, we haven't been to the moon in 50 years, at least down to the surface, right? And this is amazing. This is what we've got planned in just the next few years. We're going to start hitting the moon, and we're going to start hitting it frequently and regularly. In a lot of ways, from the orbit, from the surface, with humans, with robots, commercially, internationally. It's a whole huge campaign headed towards the moon over just the next few years. And it's really incredible to think about what that means for science. Here's a slide I show a lot when I do outreach, adults with kids, with whoever. This is just to head off this question. This is the most common question I get, I think. Why are we going back? Haven't we already been there? Haven't we already done that? The truth is, from a science perspective, no, we certainly haven't, right? We have been to one tiny little corner of the moon, right? And we did amazing stuff there. We brought back samples that we're still studying today. We're still learning from them. But there's a lot of the moon still to explore, right? We haven't been to a lot of places. And over the last couple of decades, we've sent orbiters around the moon, all kinds of instruments on them, and we've learned a lot about what the moon looks like globally, that we just didn't have that perspective in Apollo. And from that, we've learned other places that we want to go, we've learned other things that we want to do, we've learned what we missed during Apollo. And so now we have a much better idea of where we want to go and how we want to tackle the big problems of the moon. So as Barb noted, she was a member of this team. We put together a team during the midst of the pandemic, the Artemis 3 Science Definition Team, to sort of look over all the things that we've thought about over the last 50 years. Science community over the last 50 years has had a lot of time to think through what it is we want to do with the moon, where we want to go, what kind of samples we want to bring back, what kind of science we want to do in situ. And there's a lot of reports out there over the years. But now that we sort of know where we're going, now we know we're going to the South Pole, we want to put together a team just to look at what are the big questions that we can address when we go. And so this Artemis 3 Science Definition team did a fantastic job under pretty difficult conditions in the middle of the pandemic and under a really short time frame. It turned out a really beautiful report, and I encourage you all to go and read the whole report. What they came up with were these 7 main science objectives that we're looking for Artemis 3. Understanding planetary processes. That's a big, broad thing, right? There's lots of ways to address that. There's lots of things that we can do on the moon that not only helps us understand the moon, but it helps us understand processes across the solar system. The moon is our nearest neighbor. It's the easiest place to go. So if you want to study things like impact cratering, it's a great place to go and learn what the physics are of impact cratering. Understand the character and the origin of polar volatiles, something we're really excited about. This is something we totally missed during Apollo, right? We landed near the equator, had no idea about these polar volatiles, but now as we are building up our knowledge of that from orbit, we've got the Viper rover that's going to come and give us some ground truth on that. But ultimately, what we want to do is collect some of those samples and see, what those volatiles are like. Where are they? Where do they come from? How do they move around the moon? That will help us understand not only the volatile cycle on the moon, but again, how water is moving around the solar system, how we evolved, how we got to where we are. Interpreting the impact history of the Earth-Moon system. Right, so the moon, unlike the Earth, which recycles its rocks, the moon has sort of stood as a witness plate over the last 4.5 billion years, recording all of the impacts that we've had over time, right? And it turns out to be a really valuable record. of what has happened over the course of the solar system. And so learning how to read that record, bringing back samples. The other thing that allows us to do is that impact record is the way that we generally date things across the solar system on terrestrial bodies, right? So a place that has a lot of impact craters is old, right? Because it's been there a long time collecting things. It's only got a few craters, it's young, right? But we want to know more than it's young or old. We want to know exactly how old it is. And the only place we can do that is the moon, because we have those samples and can date them in our labs. So that's the where we have those tie points. And we use that to sort of extrapolate. And so the more that we can get, more of those high points that we can gather, the better we can make those connections, and the more accurately we'll be able to interpret dates on not just the moon, but on all of our terrestrial bodies. Revealing the record of the ancient sun in our astronomical environment. And the moon stands as not just a witness plate for those impacts, but it's also stood as a witness plate for the sun and all of the particles that the sun has thrown at it. And so we want to be able to look back in time and see what the sun was doing at different points in our history. Observe the universe in the local space environment from a unique location. I will leave it to talk about what that means in terms of the uniqueness of the moon and how we can take advantage of that. Conducting experimental science in the lunar environment. So S&D recently inherited a new division, the Biological and Physical Sciences BPS division, which used to sit in human exploration and now part of the Science Mission Directorate, and they have all sorts of great ideas and experiments that they also want to do at the moon and with lunar samples. And so we are also incorporating them into our plans. And finally, investigating and mitigating exploration risks. Right? If we as scientists can help the exploration side of the house do things better, safer, easier, then we get more science out of that. So it is a mutually beneficial symbiotic relationship there as well. And that's my last slide.
Wow, thanks, Sarah, so much. And next we're gonna go over to astronomy and astrophysics with Roberge.
I'm sorry?
Try the other direction.
No, there we go. It's coming. Just give it a second. I can see it. Well, I can see my slides. Okay, right. So thank you all. I'm Roberge. I am a star in the exoplanets and stellar astrophysics lab at Goddard, and I was the study scientist for the LUVOIR mission concept study, along with a terrific partner in Sean Domingo Goldman, who spoke yesterday. It's right here somewhere. Oh, there he is. And you'll hear a little more about LUVOIR in a moment. Okay, that's the lesion part. So obviously you heard a lot yesterday about the astrophysics decadal survey, and the NASA's first generation of great observatories. They span a huge swath of the electromagnetic spectrum, and honestly, they really transformed astronomy entirely. The way we do astronomy, both in space and on the ground as well. So, however, there, you'll see there, 2 of them have ended, and Hubble and Chandra are showing their age. I get a little upset about that because I'm a Hubble hugger from way back. However, the Astrophysics Decadal Survey recommended that now is the time to start working towards a new fleet of multi-wavelength great observatories. Okay, and the first one out of the gate, they said, was a total 6-meter UV optical infrared space telescope. And the key goals for this, so it's like basically it's like a super duper Hubble that would do a huge range of transformative astrophysics. But unlike Hubble, it would be designed for the key goal to look for truly Earth-like exoplanets and then search them to see if they show signs of life. And the decadal survey said, what did they say? It was, this would change our perspective on our place in the universe in a way not seen since the days of Copernicus.
And astronomers are not in general prone to exaggeration. So that was very impactful for me. Okay, so oh, that's a little formatted a little weird. Anyway, this first new great observatory was a blending of the LUVOIR and HABEX mission concepts, which were studied before the decadal. And we don't have a name yet for this new observatory, so I'm just calling it LUVEX for the moment. I just made that up, so that's not the official name. So, okay, so, but now I want to turn to another issue. Like, quoting from a different report, the search for life is both a profound and profoundly difficult endeavor. So now I want to turn to how Artemis and its infrastructure maybe can help us do this, help make this feasible and maybe easier. So just to start with, all of the pre-decadal LUVOIR and HABEX point designs need a new generation of heavy lift launch vehicles to get to their operating locations, which is out at Sun Earth L2, where all the cool telescopes want to be. So, vehicles like SLS Block 1B there, that's the LUVOIR B point design, folded up and packed up into the SLS fairing, and then with a SpaceX Starship on the right. So those are basically essential. They're enabling for this mission. But in addition to which, these new large fairings and heavy lift, they enable some interesting innovative design traits that I don't think we've fully explored yet. So the greater mass, the greater lift capacity means we can consider different materials. And the greater volume capacity puts some very interesting design traits on the table. So for example, before the decadal, we saw that the 8-meter diameter LUVOIR B design nearly fit in the Starship with its full primary mirror fully deployed. That's kind of cool. Okay, and then there's the other one. So in-space servicing and upgrading. So that was a scientific capability that kept Hubble at the forefront of astrophysics for 3 decades and is in great measure responsible for why Hubble is by some measures the most productive scientific tool ever produced by humans. The LUVOIR team felt that was really important for any new great observatory, that it's part of our scientific capability. So we did in fact design LUVOIR with serviceability in mind, as someone mentioned this morning. Modular design, standardized rails, latches, valves, that sort of thing. So, and the other thing is that multiple generations of instruments, that means multiple opportunities for new science that you didn't know about when you were designing the mission. And it also means more opportunities for partnerships, both inside the US with other institutions and internationally as well. And so finally, some preliminary work done before the decadal indicated that it may not be feasible to service an observatory, a facility as large as LUVEX in low Earth orbit like Hubble. So, but that the gateway orbit was well suited for a low delta V transfer to and from Sun Earth L2. Okay, and then finally, I'm going to say just one little thing about astrophysics from the lunar surface. And this is actually what I think, this is the idea that I'm most excited about. And so it's the idea of putting a large radio telescope on the far side of the moon. So what's cool about this? So it would allow us to pretty much for the first time observe some really long wavelengths that have been basically unexplored because they bounce off the Earth's ionosphere. So I think this is basically the AM radio, right? So anyway, so there's that. We haven't even really looked at those wavelengths before, the universe in those wavelengths. And then the other advantage is that the whole moon is shielding you from all of the Earth-based radio interference. So it's a nice radio quiet environment. So I think for me, this is like the most exciting sort of niche for astrophysics on the moon. But so there is, as you say, exciting astrophysics to do from the moon. But the part that excites me most personally is actually seeing how the Artemis infrastructure can basically be used to help everything we want to do in the future going forward. So, thanks, that's it.
Thanks, Becky. Okay, we're gonna move to Dr. McNutt, who's gonna talk about some of the enabling technologies that the Artemis program is gonna bring for science.
Can you hear me? Yes, that seems to be working. Of course, as we all know, the hardest thing about space travel is trying to get all the audio visual stuff to work, right? But maybe we're there. So let's see. This one's not mine. It's up here on the display up front.
Yeah.
Oh, okay. Gets back to my original comment.
Different size.
Nope, different one. We'll get there. It's a presentation with a film clip.
Yeah, do you have size from McNutt?
There we go.
Thank you.
And we'll get into the presentation over here in a minute. All right, so something a little bit different. This is something called Interstellar Probe. Again, I've been at the Applied Physics Laboratory of Johns Hopkins for a while now, chasing things around the solar system. And actually, could you back up to the first one again? It's a little. Oh, me. Let's see here. There we go. I've got control. That's a dangerous thing. So we've actually been working for 4 years now on a mission concept report for the Heliophysics Division as input into the Solar and Space Physics Scale Survey, which is now going to be the next one coming up after the Planetary is finished. And this was the engineering support out of APL, but we had a lot of volunteers throughout the world. There are 44 more co-authors on this report, about 146 collaborators from various institutions, I think from about 30 countries or so. And the report is actually out there on the web. If you Google Interstellar Probe as one word in APL, it should come up in your browser. It takes a little while to download. It's about 496 pages, so don't plan to read it over coffee unless you're drinking an awful lot of coffee. Anyway, what we did was to put together an overall study of what one could do. Now, this has been talked about for a while, and the teaser's already there. This is not a new idea. There's somebody named Goddard that was actually talking about this in 1918, about how could we think about ultimately getting out to the space between the stars and maybe to the stars themselves. Well, Interstellar Probe is all about getting out, doing the next thing past the Voyagers. We're not going to Alpha Centauri. That's for a different story in a different century. What this is about is getting out into interstellar space. The Voyagers, of course, are out to about, Voyager 1's out to about 150 AU. We've got about a few more years left of power on board. Voyager 1 and Voyager 2 are now going to be up to 45 years in space. Coming the end of this summer. They are running out of power, and we just really scratched the surface of the science beyond our heliosphere, which is that magnetic bubble that envelops the solar system. So the idea with an interstellar probe, this has actually been talked about and studied now going back to 1960 with a report of the National Academies. And the idea here is to take that next step past the Voyagers, actually build a spacecraft by design that can last for 50 years and get up to at least twice the speed of Voyager 1. And so the baseline goal is really to understand our habitable astrosphere. The heliosphere, of course, is one of only many constructs that are around all of those planets we now know exist out there. And to really understand our home in the galaxy, to do that, we really need to be there. We've put together with this group, a core group of about 80 people, mostly volunteers, working for a couple of years, phrasing the various science questions about really how the heliosphere interacts with the local galaxy and how the sun's activity map out to the region beyond the termination shock and through the heliosheath. and really what's going on in your interstellar space, and how does all this sort of sum together with what we have that we can see with other exoplanets, the environments that they're going to be in. And we've also been looking at a variety of cross-divisional opportunities. Of course, if you can get out there, there's possibility of doing planetary flybys, looking at dust, and doing some astrophysics observations as well, because once you get past the dust cloud that we're enveloped in the inner part of the solar system, there are pieces of the infrared spectrum that we could go ahead and take a look at that we just haven't had access to before. Now, the idea here is that, well, you could do this with a really, really big rocket. And a good example of that is the SLS. It's one of the super heavy lift launch vehicles. The example we've been looking at with colleagues at Marshall Space Flight Center, who have been incredibly helpful now for the last 3 years on this, is to look at an SLS Block 2 cargo configuration. These should be available starting toward the end of the 2020s. And basically what this is doing is changing a 2-stage rocket into a 4-stage rocket with a spacecraft on the top. And that way you can get up to really fast speeds. We've looked at what you could do scientifically with a launch optimally, probably around 2036 in August. We've taken a look at that. That gets you into the direction of the incoming interstellar wind. The spacecraft of about 860 kilograms, 1,900 pounds, about the same size as Voyager, with about the same mass, but of course with entitled totally new instruments on board. 50-year lifetime by design. That turns out to be a hard thing to do. Voyagers were designed to last for 4.5 years, so they've outlived the warranty by a factor of 10, but you still got to convince somebody that you can build something good for 50 years, and that's a little harder to do. To put a technological window on this, we had the boundary of being ready that you could launch this thing by the 1st of January of 2030. Launch opportunities every 13 months because this uses a Jupiter gravity assist to pull up the speed by about a factor of 2, getting out of the solar system. Powered by 2 next generation radioisotope thermoelectric generators. We've been working with the DOE on what is going to be available by the late 2020 timeframe, and all this fits together. And then communication, maybe as far as away as 1,000 astronomical units, so that we don't run out of bandwidth as we're going out, and maybe we can get into an extended mission as well. The other thing by design we've talked with a lot of younger people. The idea being that this would be something that you would actually by design change over the management, both the science management and the engineering management, once every decade. And so 5 decades basically of scientists and new science and new people coming in with new ideas, along with 5 solar cycles as well. And so let me just walk you through what this might look like in August of 2036 if we started the mission coming up and putting this thing together in the decade of the 2020s. This is again the Block 2 cargo with the long shroud, SLS coming out of Kennedy Space Center, and on our way on up into orbit. This piece of the video is from our colleagues at Marshall Space Flight Center, very kindly provided by them. Of course, we get up through most of the atmosphere on the solids. We'll have those come off, keep burning on the RS-25 liquid hydrogen, liquid oxygen engines to go on up, change over to the exploration upper stage with the RL-10 engines. This will take us on up to a parking orbit at about 100 nautical miles. Not going on to the moon, but rather being in Earth orbit to go around to the entry to getting up to Jupiter, so that we're in the right place to launch. The EUS will take us the first part of the way, switching over to a Centaur upper stage and switching over to a Star 48BV upper stage. This is one of the best configuration of about 170 that we looked at along with the people at Marshall. This would be a spinning spacecraft, sort of Voyager on steroids, high gain antenna, monolithic, enabled by having a large cargo hold on the SLS, 5 meters in diameter, so that we can get the data down from a long way away. We would actually be launching to a launch energy twice that of New Horizons. For the technically inclined, the launch energy here is a C3 of about 307 kilometers squared per second squared. And that could be achieved for this kind of vehicle. 50-meter wire boom antennas to look at densities, 7 months to get to Jupiter, gravity assist, past Saturn, past Uranus, past Neptune, on past Pluto, past the termination shock of the solar wind, through the Helios sheath, and to the termination shock in about half the time that it took for the Voyagers, and for a trip out for at least lasting at least out to 350 astronomical units. So anyway, this is something that could be done. It's really a question now that's up to the Solar and Space Physics Scale Survey to see if they think this is reasonable, that this could be the next great big thing in heliophysics. So again, take a look at the website, download the report. Thanks for your attention.
Okay, and we'll have Dr. Bleacher walk us through how we're incorporating some of these capabilities and use cases into the Artemis program.
All right, thanks, Barbara. Before I get started, I just, it's often important to take a moment and just remind ourselves how exciting all of this is. It's easy to forget sometimes when you're in meetings all day and discussing requirements and things like that. You can forget sometimes how amazing it is that we're doing this. Some of you may have supported the Apollo mission. Many of you in the room may have seen it. I did not. So this, for me, is a real big deal. I think it is for everybody in here. And it's important to remember that. I walked into the lobby as Dave Pierce's video was playing, and just, inspirational music, and it's good stuff. So I want to remind everybody of that. And the main theme of what I'm about to talk about is the importance of collaboration across our different organizations as we try to accomplish these big, exciting things. Big, exciting things aren't something you start preparing for before the next launch. There are things that take a good bit of time to pull together, and seeing what my colleagues have just talked about, it's inspiring to me to think about it. Just to be very clear, I'm not Julie Robinson. I work very closely with Julie Robinson. She does extend her apologies as we all start climbing on airplanes to go to meetings again. We're all reminded that the common cold is quite a thing as well. It's kind of hard to climb on an airplane when you're coughing and sneezing, even if you don't have COVID. So Julie asked me to step in. I do work very closely with her. My name is Jake Bleacher, and I actually spent a decade working here at Goddard before I took a 6-month detail at headquarters 3.5 years ago. So still there. My job as the Chief Exploration Scientist is to work closely with our science organizations, basically our stakeholders in the Artemis program, to try and help make sure that as we develop the architecture, we do it in a way that enables us to meet the objectives that everyone has. So I work really closely with Sarah at headquarters. We often jokingly call ourselves the ball bearings. We're kind of stuck in the gray area between 2 big organizations, 3 big organizations. We try to keep the machine moving as we move forward and try to accomplish these big goals. This slide here just tries to summarize some of the disciplines and highlights the mission directorates that are involved in Artemis. We use the word utilization here, just so we all understand what that means. It's really important to make sure we all think that words mean the same thing when we have conversations, especially when we come from different organizations. Utilization from our perspective means how anyone would use the architecture, how you would use a rocket to deliver a payload, how you would use a rover to get to the site you want to. So how do you use it to meet your goals and objectives? Obviously, science is a big piece of this. So that top green box there highlights kind of the big players who have voiced to us an interest in doing something utilizing the Artemis architecture. Planetary science, obviously, as we go to land on the moon and orbit around the moon. As Aki has mentioned, astrophysics. Heliophysics is a big player right now. In fact, we already have identified 2 science payloads to fly on the initial element of the GATEWA, the power and propulsion element, which is critical from our perspective to understand what that environment is like where we plan to send our astronauts. They're not going to be protected as they are in low Earth orbit on board the ISS. We know we've been out there. We know the heliophysics fleet is ever monitoring the conditions. But having those measurements on board the actual spacecraft where we plan to have our astronauts is really important. So it's kind of a double win there. It's good for us on the human exploration side. It's good for science as well. Another big player is biological and physical sciences, as Sarah mentioned, one of the new organizations that they have adopted. So understanding how biology responds to that environment. But we also interact with space operations. So what are we actually doing with our astronauts when they're up there? What are robots doing as we bring those online? Technology, maturation, and transformative technology. So working across multiple directorates here, trying to make sure that we understand the objectives that are brought to us for Artemis. But what's really critical is not just talking about it, it's actually documenting it. It's not written down somewhere and it's not agreed upon, kind of doesn't exist. So the important part is working together, meeting after meeting, trying to understand, working with our science mission director and our space technology mission director, what their communities, what their disciplines envision, so that we can think about how to develop that architecture moving forward. So to do this, we've been working on a document called the Human Exploration Operations Mission Directorate, which has recently reorged, but because we started the document in there, we are still calling it the HUMD 006 document, which is our utilization plan. So the utilization plan is where we document the objectives that are held by any stakeholder that wishes to be a part of the Artemis architecture in order to meet their objectives. The document holds those objectives, but they're owned by the directorates or the stakeholders that write them. So we don't write that section of our document. We leave it to our partners to document that. They can revise it anytime they want. And we circle back and check. You may have noticed in the green box on the prior slide, we didn't list earth science. That's because currently earth science did not indicate that they had a tremendous interest in using the Artemis architecture. That is not a closed book. We check back with them routinely just to make sure. And if they develop a plan that might use some of this hardware, then we'll work them into this document. As part of the 006 utilization plan, we have several annexes. One of those annexes, the very first one, we call the cornerstone capabilities. These are capabilities that would enable multiple objectives. And we figure this out by developing what we call use cases. So we develop use cases to explore how we would use the architecture. The first set that we've worked on are listed here: model traverses, end-to-end sample return, integrated planetary protection strategies, extended missions, integrated crew research, robotic utilization for our assets, integrated instrument strategies, and operations in cold and shadowed regions. These are kind of the big ones we're carrying right now. And what's important to understand about this is these aren't capabilities that just enable us to do one thing on one Artemis landing. These are capabilities that are needed in order to meet these big, exciting objectives. If they aren't present, we can't get to where we need to be on that path to accomplish some of these objectives. And again, we can't start to develop this before the mission that goes to do this the first time. We have to start thinking about it now so we can see how to infuse this and integrate it into the architecture as we develop it. Now I have a slide on each one of these. They're fairly word intense, so I'm just going to have a light touch on them so we can get to the questions. But the slides kind of highlight this. And again, the main message I want you to take away from this is that we are working closely with our Science Mission Directorate, Space Technology Mission Directorate partners, routinely checking back to understand, do we need to revise these? Do we need to add more objectives? Because without knowing that and documenting it, we don't know how to properly plan for it moving forward. So model traverse approaches, basically one of the big keys that we understand from our partners is that to meet big objectives, we have to be able to move around. It's not just landing in one spot and we answer the moon, right? We kind of know that already, but we do need to move around a little bit. And you saw a very similar approach throughout Apollo as they developed and delivered the lunar roving vehicle. That really opened up the capability for the astronauts to get to those diverse geologic terrains, to go deploy and make measurements and collect samples from places other than right where they landed. We already have in plans through our architecture a number of ways of meeting this. We'll be able to walk around. We have a call out right now that's under review, proposals under review for the suits to enable this. We're discussing with industry various approaches to unpressurized rovers, vehicles similar to the LRV, but that might extend for longer periods of time and be used multiple missions. Even going forward into robotic explorers and starting to think in kind of pre-formulation mode about pressurized rovers. So can we really kind of get a camper, go on that long trip, like if you want to drive from here and go check out Yellowstone or something. End-to-end sample return is a really big one. The last one, we talked a little bit about operations in cold regions. Well, Sarah already mentioned that a really exciting aspect of going to the polar region is the potential to actually encounter frozen volatiles. We'd like to bring those back. It may be that at the beginning we bring them back and they kind of volatilize in sample containers. We can't keep them quite cold enough, as cold as they are on the moon. But ultimately, we want to get to the point where we can bring back a piece of ice. That's what the science community is asking. So that requires an end-to-end sample strategy that touches almost every element that we are either building now or have even in pre-formulation. How do you take a tool and pick up a piece of ice on the moon without disrupting it, without contaminating it, without losing it, get it into a sample container, curate it, ensure that it's not going to cause any harm to anybody on our habitable volumes on the way back as it's handed from a roving vehicle to a pressurized lander, possibly passing through the gateway into a return vehicle like Orion. It's a lot to think about. It's not something we can solve in a couple of years right before we try to go pick up a cold sample. We have to think about Mars forward, planetary protection roadmaps. We want to limit our forward contamination when we do reach the point of taking astronauts to Mars, but also protect the Earth. There's a lot we can learn now on our lunar missions and in low Earth orbit to help us prepare for this, but it's something that we do have to have under control before we can take that next giant step out farther into our solar system. Extended missions. Extended missions for us are important, and we can use, again, a combination of ISS, lunar orbit, to begin collecting data on what is it like for our astronauts to spend the amount of time they will be spending in space. This is relevant for spending longer periods of time on or at the moon, as well as spending the amount of time we will need to do to go to Mars. That's the way we use this architecture, is kind of step it up slowly over time. And we're seeing this on the ISS right now, longer and longer deployments for some of our astronauts as we collect this vital data. Integrated crew research. We need to understand that process to allow NASA to coordinate and optimize research on our human subjects. Again, this is kind of studying the crew members, but what is the right way that does this in basically enabling these high quality investigations, but meeting ethical obligations to our friends, right? We're sending our friends up there to collect this information for us. They're a part of that research, but we have to do it the right way and make sure that we can get the right data. Uncrewed mobility cases. So how are we going to use robots? We have heard many ideas about how this could be done, and there are many different tasks that robotic capabilities could accomplish for us. So how do we understand how the robots operate on their own? How do they integrate with crew activities, all to meet the kinds of objectives that we're talking about? Maybe a robot goes and collects that ice cube. Maybe it's not right for us to send an astronaut, a warm body astronaut. We don't know yet, but the use cases are what help us drive to the point of being able to study this and know that it's something we need to accomplish. Integrated instruments use cases. Some of the measurements you heard about from our colleagues are going to require us to launch big heavy things and get them out away from the Earth and maybe even out of the solar system. Some of it is going to be trying to have instrument packages that make complementary measurements as we move around on the lunar surface or in orbit around the moon. But we have to think about what's the right cadence, sequence of deployment for these things and how they'll work together to get us the answers that our science and technology communities are looking for. And then the last one, complex operations in cold and shadowed regions. I already talked a little bit about this, but I think you probably all understand that walking into permanently shadowed regions is a big task for us. In Apollo, we did walk through shadows. We have data on suits operating in shadows. But these permanently shadowed areas, the places, where we want to get the really cool stuff, the ice cubes, the really cool data, they're hard to get into, both for robots and for astronauts. So we have to start thinking this through now. What are the right ways to even get in there so we can start thinking about that in the sample process? I think that's my last slide. I do appreciate everybody's time and back to Barbara.
No, thanks, Jake. Okay, we're gonna open it up to some audience questions. So while you are thinking about that and raising your hands, I just wanna pose one question to the panel. Can you talk a little bit more about the permanently shadowed regions and the special, not just the permanently shadowed regions, but the special regions of the pole, the lighting, the thermal conditions? How does that open up new science, and what do we have to think about when we're going there?
Looks like everybody turned their head with me, so I'll go ahead and take that one. But this is something that Sarah and I talk about frequently, as well as all of our colleagues. And it's a really important point. When we were told, given the direction to land at the South Pole of the Moon, we were told we're going there initially for 2 resources. The first of those is light. There are places on the lunar surface with greater than average amounts of light, which is ideal for us for power, as well as thermal control, as Barbara just mentioned. And then the other resource would be going for the volatiles. So the volatiles are of scientific value to us, potentially resource value. So understanding that volatile environment is really key. The processes that drive how volatiles are preserved, do they migrate, things like that. But the lighting at the moon, if we step back to that, I think to Barbara's point, is really complicated. I think everybody here probably knows that, but probably doesn't know exactly how complicated. And we are studying this extensively right now, in large part with collaborators at Goddard working from the Lunar Reconnaissance Orbiter team. But at Apollo sites that were near equatorial on the near side, the lighting there operates in a predictable manner over large surface areas. So a lunar day is on the order of an Earth month, and you have about half of that time in continuous darkness, half of that time in continuous light. So you can prepare a mission to go for a week or 2 weeks or even 3 weeks, and you know what the lighting will be like in a given area. At the poles, because the light is coming in at a very oblique angle, if you were standing on the pole, the sun never goes above about 1.5 degrees above the horizon, and it will be below the horizon sometimes. And so what happens is, at any given spot, the ratio of light to dark is not a 50-50 split. Okay? It ranges from complete darkness, permanently shadowed, to places that are, we think, on the order of about 80 to 95-ish% sunlight. And what's really hard about that is that that ratio changes over very short surface distances. So unlike at Apollo, where it's 50-50 split here, it's 50-50 split 10 kilometers away, here you can go from almost permanent light to complete darkness in a very short distance. So we have to really model and understand that for thermal controls, know how long you're going into a dark stretch. If you want to go get the volatiles that are preserved there. This is a really important area that we're studying right now to get a handle on that.
I will say that it's also going to be a really tricky place to do geology. It won't look like Apollo where the sun was high overhead all the time. See if you were doing. We're actually out practicing, going out in the middle of the night and to geologically relevant places and like bringing our own lights to try to figure out what kind of light system you need on your suit, what kind of light system you need around you in order to be able to see what you're doing, in order to be able to do that geology. It's something we really got to think through. It's very different than the way that we have, the way that normal geologists do field work, right, and the way that Apollo operated. And so we are spending a lot of time practicing right now to get ready for that.
The runners over here, come on, steal the microphone from these folks.
Yeah, put your hands up if you've got questions, and you do. Please do.
This is addressed to whoever that's
Turn your mic on.
Sorry.
All right, so my question is about powering all of the different projects going on, especially since we have humans. So I was wondering how, if Artemis plans to tie the kilopower project into it. And I also had some questions about kilopower, but I'm not sure if because I was wondering why in most of its concept images it has a solar array, and why not use the energy from the turbines to power the pumps and mechanisms.
Guess that's me again. Yeah, I think this panel is probably not the right group. I know Nikki was here, working with folks from STMD is where we get the solutions that you're talking about. Right now, what we are trying to do is understand from our partners what are the tasks we need to accomplish, and then understand how much power we expect that to take. The solution space is still somewhat open, so we do work with STMD about how are we going to solve those power needs. The early missions, the very early Artemis missions, will largely focus on solar power. But I just want to be real clear, we are exploring the options that you mentioned as well. But we don't have that plan that in place that far ahead in the architecture.
Okay, thank you.
We have a question from online.
Yeah, hi. So could you please talk a bit more about the advantages of robotic lunar sample capture over human sample capture in terms of planetary protection?
Sarah, is that you?
Yeah, humans are dirty. Whenever we go, we bring a lot of our own ecosystem with us. So if you can use robotics, keep the samples away from the dirty humans, it is much better for planetary science. So planetary protection. So yeah, so we can clean a robot, but it's very hard to clean people.
Yeah, and then another aspect to that is that we'll send crew for limited periods of time, especially initially. Robotics might be able to operate for much longer periods of time. So again, it really depends on how we want to partner human and robotic capabilities. There may be places we don't want to send the humans, and there may be places that the humans are the right hate saying this, the right tool to get the job done. The ability for the astronaut to think rapidly and make rapid decisions is critical, especially I think with things like volatiles that could be lost. So how do you have the human there? Maybe they need to be in situ on site, maybe they're operating the rover or robot from close by. But how do we take advantage of the best of the capabilities that mix between the robotics and the astronauts is the key thing we're trying to understand.
Yeah, and if I could just jump in here too, in terms of planetary protection, of course, we don't think there is indigenous life on the moon or that's ever evolved on the moon. But it makes it a really interesting end case, and you heard about dragonfly, that we talked about earlier, where you have organics mixing with water. We don't think there was a lot of liquid water ever on the moon, but there's clearly organic molecules there that have come from exogenous sources or that have been formed there by interaction of the rocks with the solar wind. So it's a super interesting end case for what happens when you have organics on a planetary surface being irradiated, having these kinds of physical interactions, but not leading to life. And it's going to be a nice way to bookend some of our other life detection cases. Other questions?
Yeah, I just coming back to what Jake was just talking about. With these astrophysics telescopes out at Sun Earth L2, if you were going to service them there, you're probably talking robots. But then I think about the servicing of Hubble, and when I think it was John Grunsfeld had to grab the thing and just yank it because it wasn't coming out. So when I think about that, I think it makes me think like, there's kind of something that would be kind of wonderful about being able to do this at Gateway as sort of like as a telepresence, but just in case, having a very adaptable tool available that can just, put some muscle into it or kick the side or something. So.
I have a question for Ralph on an interstellar probe. Are you going out of the solar system in the same direction as previous probes? And does that matter to the science?
Again, it's always the audio-visual problem. So one of the things that we did was we looked at a variety of different directions that you could go in. Basically on this study, what we were doing was putting together a menu of what one could, in the future, do some down selects on. And this was not a science and technology definition team effort. And so there's a lot of debate about that. And ultimately, if this were to go forward, one would need to put together an STD to make some decisions. One of the things that we looked at was the fact that, of course, these days one can build energetic neutral atom cameras that we've been able to actually take pictures of things with energetic neutral atoms. The IBEX ribbon and the upcoming IMAP mission for being able to look at the interaction region in energetic neutrals is, of course, a big new technique. Something that did not exist with the Voyagers. And so what one could think of doing is going out slightly to the side of the direction of the incoming interstellar wind, where you could look back and take a picture of the entire heliosphere from the outside in energetic neutral atoms and really be able to see what this bubble looks like. I mean, it's been described as everything from a windsock to a spherical slope bubble, and then the debate continues to rage on, and it probably will until one is able to do something like that from the outside. So what we've done in the report is to try to outline the possibilities, and again, is input into the decadal survey, and deciding exactly what one would do. First of all, one has to decide one wants to really do the mission, and then there needs to be some more debate about that, about exactly which way to go.
I think we have time for one more.
Yeah, could you say something more about L2 in the sense that I hear that there are some proposals coming in for more missions there and stuff, and so the first squatters, where how much fuel might be needed if you can't be in the best spot and things like that. Just how the dynamics of it might work.
Okay, so I can tell you why the telescopes want to be there.
I know why they want to be there, but
Yeah.
the cost of the mission, the second the risers.
I don't know. I mean, it's not crowded. I mean, space is a big place. I think, I would think there's plenty of room for L2 halo orbits, for pretty much everybody, but honestly, I'm no, orbital dynamicist, so, someone else will have to answer that.
So you did mention that it's a place that you can get to from the NRHO that gateways can be in. Does that help you get there? Does it help you go to the V-wise to go from the?
Oh, for sure. I mean, because we got out of the hard part, or it's gravity well, and going back and forth from gateway type orbit to Sunroof L2 is not much delta V. So that part is good for sure. But other than that, I don't think I can answer that in any more detail.
One more, if you can be very quick.
So can you comment, kind of review again for the telescopes, going from what we can launch right now to super heavy, how much more capability that gives, and then going beyond that, even what would you do? In terms of assembly, is there possibilities for that?
Okay, so actually I'm going to jump to the second part of that because that's what I'm going to talk about. Assembly, yeah. So I talked about servicing and upgrading, but obviously, it's occurred to people that what if we might want to put it together in space? So I guess my question, and I have to say, several years ago when I was first hearing about this, I said, well, I believe you can assemble a telescope in space, but I don't believe you can assemble a good one. But then I spent some more time with engineering colleagues who convinced me that I was probably wrong about that. However, I don't think we don't have really a very good idea of what tools, infrastructure, or approach or methodology or anything about how we would do that. So I would leave this as sort of like a challenge to the audience to start thinking.
Awesome. Well, thank you, everyone. It's been a pleasure to be here with you this morning.
Thank you very much.